Hello everyone. In today's lecture, we'll be continuing our journey with the communications course, and today we'll start in a new chapter, which is the pulse modulation. And as we're going to learn in this chapter, that the pulse modulation is basically a transition from analog to digital communication systems. Basically, in the previous chapters, we have seen what's called the continuous wave modulation, basically AM, FM, and PM, in which we had a sinusoidal carrier and we choose one parameter of this carrier, so basically amplitude, frequency, and or phase. And this parameter is basically changed continuously in accordance with the message M of t. In this chapter, we'll be dealing with a different approach, which is basically instead of having a sinusoidal carrier, now we have a train of pulses which acts as a carrier, and one parameter of this train of pulses will be varied in accordance with the message. The other difference here is that we do not deal with the message M of t as is. Rather, we would be sampling this message, transforming it from a continuous time signal into a discrete time signal before we can do the pulse modulation, as we're going to see later on during this lecture and the next lectures. Basically, there are two families of pulse modulation. One is the analog pulse modulation and the other one is the digital pulse modulation, and we're going to see the difference later on. In analog pulse modulation, we have a periodic train of pulses. This train of pulses acts as the carrier wave. And we basically change the characteristic of this train of pulses in accordance with sampled version of the message. So basically, the train of pulses has three features or characteristics: the amplitude, the duration of the pulse, and the position of the pulse. So basically, we sample the message M of t, transform it into a discrete time signal, and then we use the sample values to control the amplitude. In this case, it's called pulse amplitude modulation. Or we change the duration of the pulse in accordance with the sample of the message. It's called pulse width modulation. Or we change the position of the pulse in accordance with the sample value of the message, which is called the pulse position modulation. In analog pulse modulation, the information is transmitted in an analog form, but the transmission takes place at discrete times. This basically means that M of t is first transformed into a discrete time signal, so we introduce discreteness in time. And then we do not put any restriction on the amplitude, so the amplitude can take any value, and hence the information is transmitted in an analog form. This means basically we do not restrict the amplitude to discrete values, but the time is discrete in a way. We force discreteness in time through sampling process. On the other hand, in digital pulse modulation, the message is forced to be discrete in both time and amplitude. If you remember from the previous course, we had the signals and systems. The difference between discrete time signals and digital signals is basically the discreteness in the amplitude. In discrete time signals, we have discreteness in the time, but the amplitude can take any value. But in digital signals, we have discreteness in the time and in the amplitude. The amplitude is allowed only to take discrete values. This is what's happening in digital pulse modulation. In digital pulse modulation, we have discreteness in both time and amplitude. And in this case, we can use the so-called pulse code modulation, or PCM, or coded pulses, as you can see here. And we will see this later on during the chapter. So in this chapter, we will be talking about the following topics. First, we will cover the sampling process, and we will see how the sampling process affects the spectrum of the signal. Next, we will talk about the pulse amplitude modulation, which is a famous form of analog pulse modulation. And then we will move to the quantization process, which results in the discreteness in amplitude. And now we will be ready to talk about the digital pulse modulation and with the famous modulation technique, which is the pulse code modulation PCM. And by the end of the chapter, we'll be talking about time division multiplexing. And of course, this is tentative because depending on how much time we're going to have, we're going to cover the topics. So let's start with the sampling process. In uniform sampling process, we convert continuous time signal into a discrete time signal by basically taking samples at uniform or equal distances or spaces in time. So in uniform sampling, we take the value of the signal at, let's say, time 0, and at time equals Ts, and 2Ts, 3Ts, and 4Ts, where Ts is a sampling interval or sampling period. That's why it's called uniform sampling, because the samples are uniformly spaced in time. And now the question comes up, which is how we are going to choose a sampling rate. What is the proper sampling rate? Because let's say we are sampling a human voice. Is it enough to take 10 samples per second, or 1,000 samples per second, or 10,000 samples per second? What is the appropriate sampling rate? In order to answer this question, we need to do some mathematical analysis. But the main idea is that the faster the phenomena you're trying to sample, the higher the sampling rate is. If you're sampling a slow phenomena, you will need less samples. If you're sampling a faster phenomena, you will need larger number of samples, as we're going to see. So let's consider an arbitrary signal g of t, and this signal is continuous time, so it's basically defined for all time instants. And let's define the spectrum of this signal to be g of f. And g of f can be obtained using Fourier transform, as we know, where g of t is transformed into frequency domain to be g of f. You can obtain this through the famous Fourier transform equation, which is the integration from minus infinity to positive infinity g of t e to the negative j 2 pi f t dt. So we're having a general signal g of t and its spectrum g of f, and we will see how sampling g of t in time domain will affect the spectrum. So we're talking about the frequency domain consequences of the sampling process. This basically will open up some topics, basically what is the appropriate sampling frequency, how to reconstruct the original signal from this sampled version, and so on. So suppose that we sample this signal g of t instantaneously at uniform rate once every ts. As we said, in uniform sampling, we take sample every ts seconds. And by instantaneously, or here in the title, instantaneous sampling, we mean that the sample value corresponds to one instant in time, exactly t equals ts or 2ts or 3ts, as opposed to the so-called natural sampling. In natural sampling, it's kind of different because the time here expands a little bit beyond ts. We're going to see it later on. Okay, so consequently, we obtain an infinite sequence of samples spaced ts seconds apart, and it's noted by g of nts. N is an integer, positive or negative, so if n equals 0, we get g of 0, n equals 1, g of ts, g of 2ts, and so on. So we're getting discrete values in time, and time, instead of being t, now it's nts, where n is integer. So we're having time right now 0 ts, 2 ts, 3 ts, 4 ts, and so on. And as we discussed previously in signal systems, we will drop ts and we'll get g of n as a discrete time signal. Ts is called the sampling period or sampling interval. Fs is called the sampling rate. It's basically 1 over Ts, the reciprocal of Ts. And this ideal form of sampling is called instantaneous sampling. This figure basically illustrates the idea of sampling. If you have g of t, a continuous time signal, and we want to sample this signal, so basically we are as if we are multiplying this g of t with train of impulses. So let's see this function here. This is at time 0, so as if we have an impulse delta of t, and this delta of t is kind of multiplied by g of t, so it will kill all the values of g of t except at the time instant t equals 0. So we'll be getting delta of t multiplied by g of 0. So the strength of this impulse, the area of this impulse, is basically g of 0. For instance, this is an impulse at 3ts. So this is delta of t minus 3ts. And the strength or the area under this impulse equals g of t at 3ts. So the sampling process, the instantaneous sampling process, can be mathematically modeled as if we're multiplying g of t, the signal to be sampled, by or multiplied with a train of impulses, delta of t minus nts, and these impulses are equally spaced at ts, 2ts, 3ts, and so on. And the resulting discrete time signal g delta of t, the sampled version of the signal. So let g delta of t be the signal obtained by individually weighting the elements of a periodic sequence of Dirac delta functions spaced ts seconds apart. So basically we are trying to describe this equation here. G of nts is the values of the signal g of t at instants nts, and delta of t minus nts represent pointers or arrows to a specific time instance. So let's say we put n equals 0, we get delta of t, and it's an impulse located at time t equals 0, and the weight or strength of this impulse is g of 0, which is a sample value at time equals 0. Let's put n equals 1. We get delta of t minus ts. So it's an impulse located at t equals ts. We multiplied by g of ts, which is the sample value at ts, and so on for n equals 2 or 3. So this summation basically is saying we have a sample value of g n ts located at time t equals n ts. And this is again called an instantaneous or ideal sampled signal. And if you remember from the signals and systems course, an impulse is basically a rectangular pulse whose width is delta t and whose height is 1 over delta t, so the area is 1. So in this case, if the impulse is multiplied by a factor g of n ts, it basically means a rectangular pulse of duration delta t and height g of nts over delta t, which makes the area under this impulse g of nts. So the area or the strength of this impulse represents the sample value we're looking for actually. So to proceed with the mathematics here, we need to model the sampling process as follows. We will define a train of impulses, a function p of t, which is a train of impulses, summation from n equals minus infinity to positive infinity, delta of t minus nts. If we try to sketch this function, it will be an impulse at t equals 0 with strength equals 1, an impulse at t equals ts, strength 1, impulse at t equals 2ts, 3ts, and so on, from minus infinity to positive infinity. We're having a train of impulses all with the same strength, which is 1. This train of impulses, p of t, is multiplied by the signal g of t, which is the signal to be sampled, resulting in g delta of t, which is the impulse weighted with the sample value. Delta of t with weight g of 0, delta of t minus ts with the weight g of ts, and so on. So we get g of t multiplied by the summation delta of t minus n ts. When you and as we have seen previously in the signal and systems course, when you multiply a function with an impulse, you are left with the function value at the impulse. So now instead of having g of t, now we have g of nts multiplied by the impulses. So basically each impulse will have the sample value corresponding to the time instant at which the impulse happens. Okay, keeping this in mind, the objective here is to determine the spectrum of the sampled signal, or in other words, to try to find what kind of consequences we have in the frequency domain due to the sampling process. To proceed, we will need to deal with P of t first. So P of t, if you notice, is a periodic signal. It's kind of periodic. It repeats itself every ts. We have an impulse at time equals 0, impulse at time equals ts, 2ts, 3ts, ts, minus 2ts, and so on. So it's a periodic signal. All impulses with the same strength, same value, 1, 1, 1. So we're going to be using Fourier Series. Fourier Series is a tool used to represent periodic signals. So we want to basically express P of t as a summation of Cm, which is kind of a constant or coefficient, times e to the power j2 pi m fs t. Ts is a fundamental period. Ts is a fundamental period, and fs is a fundamental frequency. It's basically 1 over Ts. So here, the frequency in this term is m times fs. If m equals 0, this is a DC term. If m equals 1, this is a fundamental frequency, or the harmonic, first harmonic. If m equals 2, the frequency is 2fs, which is the second harmonic, and so on. And now we need to find Cm. And Cm, if you remember from the signals and systems, can be obtained as follows. It's basically 1 over the period, 1 over Ts, and then you do an integration over one cycle, one period, of the function times e to the negative j 2 pi m fs t dt. And note here that I have chosen the integration period to be from negative ts by 2 to ts by 2. The point here, if you remember from signals and systems, if we have an impulse, we need to have the impulse in the middle of the integration interval. So P of t is train of impulses. We have an impulse at 0, at ts, at 2ts. Now, if we choose the interval to be from 0 to ts, for instance, we will be having a problem because we have an impulse at 0, another impulse at ts. But now that we have chosen the interval to be from minus ts by 2 to ts by 2, the impulse is lying in the middle of the integration interval. Now it's going to be easier. So in the interval from minus ts by 2 to ts by 2, P of t is basically an impulse delta of t. And now we have an impulse multiplied by a function, which is this exponential function under the integration. And as we have seen before, the integration of an impulse multiplied by a function equals the function evaluated at the time instant where the impulse happens. So this impulse happens at t equals 0. So basically this integration equals e to the power 0. You put t equals 0, which is 1. That's why Cm equals 1 over Ts. Now we can write P of t as a summation of 1 over Ts e to the j 2 pi m fst. Something like this. So basically now the sampled signal g delta of t is g of t times 1 over ts summation e to the j 2 pi m fs t. Now we can use the Fourier transform to obtain the spectrum of g delta of t. So g delta of f, the spectrum of g delta of t, is a Fourier transform. Integration g delta of t e to the negative j 2 pi f t dt. Now we replace g delta of t with this expression, g of t times 1 over ts times the summation. So we have a summation and an integration, and the usual trick is to replace or interchange the integration with the summation. If we take the summation to be outside and the integration to get inside, you'll get this form, 1 over ts summation from minus infinity to infinity integration of g of t e to the negative j 2 pi f minus m f s t, where we have combined the two exponentials we have, the exponential from the Fourier transform definition and the exponential from the Fourier series expression we had before. So if you take a look at this integration, it's very similar to the Fourier transform. In Fourier transform, you integrate minus infinity to positive infinity g of t e to the negative j 2 pi f t dt. So in the definition of Fourier transform, we do not have this mfs. So if we think for a second that we will ignore this term for a second, this integration will give us g capital of f, the spectrum of g of t. But now, since we have f being replaced with f minus fs, minus mfs, now instead of having g of f, we will have g of f minus mfs. And now we come to the important result of this mathematical analysis, that the spectrum g delta of f, which is the spectrum of the sampled signal, is equal to 1 over ts or fs summation of g capital, which is the spectrum of the original continuous time signal, of f minus mfs. So what does this equation say? Let's try to take a closer look. Let's put m equals 0. If m equals 0, we get g capital of f, which is the spectrum of the original continuous time signal. What if we put m equals 1? You will get g of f minus fs, which is the spectrum of the original analog signal shifted in the frequency domain by fs. What if you put m equals 2? We get g of f minus 2fs, which is the spectrum of the original signal shifted by 2fs, and this goes all the way to infinity. If you put m equals minus 1, you get g of f plus fs, which is the original signal spectrum shifted to the left at minus fs, and this goes all the way down to negative infinity. So this summation basically says that the spectrum of the sampled signal is exactly the same as the spectrum of the original signal, but shifted at 0, fs, 2fs, 3fs to infinity, and minus fs, minus 2fs up to negative infinity. So the direct result of sampling in time domain is periodicity in frequency domain. The spectrum has become to be periodic, and the period is fs. The other consequence is that the spectrum is multiplied by fs, the sampling frequency. That's why if you note in MATLAB, if you use FFT, the fast Fourier transform, or any signal, the spectrum will be very large, has very large amplitude. It's the same shape you're expecting, but the amplitude will be very large because it's basically multiplied by the sampling frequency. So in MATLAB, after you use fast Fourier transform, probably you will be needing to divide by fs in order to get the actual spectrum values. Okay, so this equation basically means that uniformly sampling a signal results in a periodic spectrum. And this result is very important. It's a well-known result in signals and systems and in DSP that discreteness in time domain results in periodicity in frequency domain. Again, discreteness in time domain, the sampling we have introduced in time domain, results in discreteness in time domain. This results in periodicity in frequency domain, and the period would be fs, the sampling rate or the sampling frequency. Now, if the signal g of t is assumed to be strictly band limited, this basically means that the spectrum g of f equals 0 for magnitude f larger than w, where w is the bandwidth of the signal. So if g of t has a limited bandwidth w, and it is strictly band limited, that the spectrum is exactly 0 for f larger than w or less than minus w, then we can illustrate the relation between g of f and g delta of f as follows. In this figure, Here, this is g of f, the spectrum of the original signal. And here we have the spectrum g delta of f, which is the same as g of f, but repeated at 0, at fs, 2fs up to infinity, minus fs, minus 2fs up to down to negative infinity. And here, the amplitude is multiplied by 1 over ts, or by fs. So, as you can see here, this is the spectrum of the original continuous time signal. This is the spectrum of the discrete time signal after sampling. So sampling resulted in periodicity in frequency domain, and the period is fs. Two concerns come up here. The first concern is, what guarantee do we have that this repeated spectrum will not overlap with the original spectrum? One might ask, does it matter if the spectrum overlap or not? It does matter, and this basically brings us to the next concern, which is, how can we reconstruct the original signal from this spectrum? Because don't forget that we do the sampling in order to transform analog signals into digital signals to be processed by a computer or stored or transmitted over the internet, but at the end of the day we need to reconstruct the original analog signal from the discrete time signal. So to answer the second question first, we can use a filter. This kind of filter will allow frequencies from -w to w to pass and will kill any other frequency outside this band. So if we apply this discrete time signal to this filter, what's going to happen is that all the repeated spectrum at fs, 2fs, 3fs, minus fs will be killed, and only the spectrum between -w and w will pass. And this is basically the spectrum we are looking for, the spectrum of the original signal. So if you pass this spectrum, this signal, to this filter, you will get this spectrum. In other words, if you pass a discrete time signal into this kind of filter, you will get a continuous time signal. And this filter is a low pass filter. It allows the low frequencies around 0 to pass. So this is how we're going to reconstruct the original signal. The other concern is, does this spectrum overlap or not? It's clear, of course, that if the spectrum overlap, if this spectrum overlaps with this spectrum, we will not be able to reconstruct the original spectrum because there will be some sort of interference, right? If this spectrum overlaps with this one, we'll get interference, and we will not be able, even using this filter, to reconstruct the original signal. So this kind of interference is to be avoided. So what kind of condition we can have to avoid this interference? If you take a closer look here, we want to make sure that the edge of this repeated spectrum is always larger than W. If this edge is less than W, then the two triangles here will overlap and the spectrum will overlap. So the edge of this triangle or this spectrum here is Fs minus W. So we always want Fs minus W to be larger than W, which means Fs larger than 2W. Okay, so the mathematical tool used with discrete time signals is called the discrete time Fourier transform, and now might be a good time to discuss the relation between discrete time Fourier transform, sampling, and the continuous time Fourier transform. This will help us later on with the sampling and reconstruction, and also will establish the mathematical foundation for the DTFT. So the DTFT can be derived as follows. So G delta of f, which is the spectrum of the discrete time signal, the sampled signal, can be basically obtained as the inverse Fourier, as a Fourier transform of G delta of t. Integration G delta of t e to the negative j2 pi f t dt. But G delta of t is basically a summation of G of NTS, which is the sampled signal, the sample value, multiplied by delta of t minus NTS. And again, we'll be interchanging the summation and the integration. Summation will be get outside g of nts, and then the integration get inside delta of t minus nts e to the negative j2 pi f t dt. Now note that we have taken g of nts outside of the integration because the integration is with respect to time t, and g of nts is not a function of time. So this integration is an impulse multiplied by a function, and as we have seen previously, this integration will give us the value of the function at the instant where the impulse happened. So this impulse happened at time t equals nts. So this integration will be the value of this function e to the negative j2 pi ft, but we replace t with nts. So this integration is basically e to the negative j2 pi f nts, which will give us summation g of nts e to the negative j2 pi f nts. Of course, Ts is equal to 1 over Fs. So now we can put e to the negative j2 pi f over Fs. And now we will define a new frequency, capital F. This new frequency equals f over Fs. So in continuous time signals, we use f small and omega small to represent the frequency. Whereas in discrete time signals, we use capital F and capital omega to represent the frequency. Capital F is basically a normalized version of F small. F capital equals F small over Fs. And of course, as we have seen in signals and systems, we usually represent g of nts as g of n. Now it's a discrete time signal. Of course, e to the negative j2 pi fn is equals to e to the negative j omega n, where capital omega is equal to 2 pi capital F. And this is the definition of the discrete time Fourier transform. So this definition is actually, you can find it in textbooks, online, and anywhere. It's kind of a definition that gets the spectrum of discrete time signal. And this definition is based on the sampling and the Fourier transform, the continuous time Fourier transform. This being said, we'll go back to the sampling process. As we have discussed previously, in order for the spectrum to be far apart and not to overlap, the sampling frequency must be chosen to be larger than 2w, where w is the bandwidth of the signal. In this case, there will be no overlap in the spectrum of g delta of f. Therefore, the original spectrum is intact, i.e. there is no interface, no interference, and then g of t can be perfectly restored from the sampled signal. Let's go back to the figure here and discuss it one more time. We want to avoid overlap, so we want this edge, which is fs minus w, minus w, to be always larger than w, which means fs larger than 2w. In this case, the spectrum will not overlap and we can reconstruct the original signal using a low-pass filter. But if the sampling frequency is less than 2w, there will be overlap in the spectrum. We will get a distortion that's called aliasing distortion, and the spectrum will be aliased, and we will not be able to reconstruct the original signal from the samples. This is called the aliasing distortion, and we will talk about the aliasing a bit more later on. Fs equals 2w. W is the bandwidth of the signal, is known as the Nyquist trait, and Ts equals 1 over 2w is called the Nyquist interval. In order to avoid aliasing, in order to avoid this overlap in spectrums and interference, the minimum sampling frequency should be chosen to be equal to 2w, to the maximum frequency content or the bandwidth of the signal. And assuming that Fs is larger than 2w, so assuming we do not have aliasing distortion, we do not have any overlap in the spectrum, we need now to talk about the reconstruction of the original signal. So in order to obtain g of t is the inverse Fourier transform of g of f. So integration minus infinity to positive infinity g of f e to the positive j2 pi ft df. But we know that g of f is assumed to be, since g of f is assumed to be strictly band limited, that is, g of f equals 0 for frequencies larger than w and less than minus w, we can simply replace the limits of the integration to be minus w to w. But if you take a look at the figure, the previous figure, g of f in the interval from minus w to w is actually equal to g delta of f, the spectrum of the sampled signal. So we can replace g of f with ts g delta of f. Let's go back to the figure and take a closer look. So here, in the interval from minus w to w, g of f and g delta of f are exactly the same except for a scaling factor, fs. So what we did in the integration is that we replaced g of f with g delta of f, but someone might say, okay, but g delta of f has this repeated spectrum which does not appear in g of f. Exactly, you're correct, but since we are integrating from minus w to w, then in this integration interval, g of f and g delta of f are exactly the same except for a scaling factor. This allowed us to replace g of f with g delta of f with this scaling factor ts. Now g delta of f is equal to the summation of g of nts e to the negative j2 pi n tsf. This equation basically comes from the discrete time Fourier transform. If you take a closer look at the discrete time Fourier transform derivation we had here, g delta of f is summation g of nts e to the negative j2 pi f n ts. So here we have this summation, and again we will combine these two exponentials together and replace the summation with the integration. So we have ts summation g of nts integration from minus w to w e to the j2 pi f t minus n ts. If you evaluate this integration, you will get the sinc function. So g of t, the original continuous time signal, is related to the sampled version g of nts by this equation. If we take a closer look at this equation, at n equals 0 we have a sinc function, sinc 2wt. So the maximum or the peak of the sinc happens at t equals 0, and it's weighted with the value g of 0, the sampled value at 0. And then if n equals 1, you get sinc 2w of t minus ts, which is basically a sinc function shifted at ts, and the peak value equals g of ts, which is a sample value. And at the same at n equals 2, you have a sinc function sinc 2wt minus 2ts, sinc shifted at 2ts, and the weight is g of 2ts. And this happens for all the samples from minus infinity to positive infinity. So what's happening here is sort of interpolation, and the interpolating function is the sinc function. So as if we have these samples and we want to reconstruct the original signal, we do sort of interpolation using a sinc function. We shift the sinc function at a different time instance. Every sinc function will have a weight equal to the sample value. Add all these together and you will obtain the original signal. So now each sample is multiplied by a delayed or shifted version of the interpolation function, the sinc function, and all the resulting waveforms are added together. The previous equation can be seen as sort of a linear convolution between the discrete time signal g delta of t and the impulse response of the low pass filter h of t. Remember that here we had a low pass filter that we used to reconstruct the original signal. This low pass filter is a rect function. If you do an inverse Fourier transform, you will get a sinc function. So the impulse response of this filter, ideal low pass filter, is a sinc function. So the impulse response of this filter would take this form: 2wts sinc 2wt. So this is the frequency response, the rect function, and the Fourier transform will be the impulse response, which is h of t. So if we do the linear convolution between h of t and g delta of t, we supposedly will obtain a g of t, the continuous time signal. How's that? As we have seen in signals and systems, the Laplace transform multiplication in S domain corresponds to linear convolution in frequency in time domain. So what's happening here when you filter a signal, you multiply the spectrum of the signal with the frequency response of the system, and this is equivalent to convolving the signal with the impulse response. In other words, if we have an LTI system with an impulse response h of t with an input g delta of t, the output is a linear convolution between the input and the impulse response. So this is the filter, impulse response. This is the input signal, convolution, you get the output signal. So integration minus infinity positive infinity g delta of tau h of t minus tau d tau. But g delta of t is the summation of g of nts times delta of tau minus nts. Now we will exchange integration and summation. We will get this integration here. So we have an impulse multiplied by a function, and again this will result in the value of the function evaluated at the instant where this impulse happens. But keep in mind that this integration is with respect to the variable tau, not t. So this impulse will happen at tau equals nts. So the integration will be the value of h, but we need to replace tau, not t. Replace tau with nts. So this will give us h of t minus nts. So g of t will be summation g of nts h of t minus nts. H is the sinc function, so we will get the same exact expression we obtained previously, which was the interpolation equation we discussed previously. Again, the sinc function shifted at 0, ts, 2 ts, 3 ts, and it has a weight which is equal to the sample value, which is g of nts. Okay, this implies that the original signal can be reconstructed using a low-pass filter, reconstructed from the samples we have. Given that the signal is band limited, of course, and the frequency response of the filter is happening between minus W and W. This filter is known as the reconstruction filter or the synthesis filter. But this filter, with this configuration, the ideal filter we have, is not physically realizable because it's non-causal. How we can judge the causality? If we look at the impulse response, h of t, it's a sinc function extending from minus infinity to positive infinity. For a system to be causal, if you remember, the impulse response has to start at t equals 0. If the impulse response starts before time equals 0, then the system is not causal. So this ideal filter cannot be implemented physically. That's why we need to look a little bit deeper into this situation. But before we do that, let's state what we have right now. Let's summarize what we have. So the sampling theory basically says that a band limited signal that has no frequency larger than W is completely described by specifying the values of the signal at an instance of time separated by Ts, which is 1 over Fs, and Fs is chosen to be larger than 2W. It basically says continuous time signal, a band limited continuous time signal of bandwidth W, is completely characterized by the samples taken at instance nTs, where Ts is 1 over Fs and Fs must be larger than 2W, the bandwidth of the signal. Or equivalently, a band limited signal that's band limited to W and minus W is completely recovered from the samples if Fs is chosen to be larger than 2W. So the two statements basically say that a band limited signal that's limited to W bandwidths can be completely described and recovered from the samples given that the sampling interval is Ts equals 1 over Fs and Fs is chosen to be larger than 2W. That's why if you sample a human voice usually has a bandwidth of 20 kilohertz. So the sampling frequency should be larger than 40 kilohertz. So if you check the property of any audio file you have in your PC, the sampling frequency will be kind of 44,000 samples per second, which is slightly larger than 2 times 20. Here we have three problems. I will leave these to you guys to work on, and in the tutorial you can use them. Uh, Basically, you're asked to specify the Nyquist rate with a sampling frequency. In this case, you will need to find the spectrum of the signal, and then the Nyquist rate is 2 times the bandwidth. And most of these functions are sinc functions, so it goes to the frequency domain as rect function. You will have the bandwidth very easily. So let's move on. As we have discussed before, the sampling might result in the so-called aliasing phenomena. So in the previous derivation, we have assumed that the signal is strictly band limited, that the spectrum G of f is 0 for frequencies larger than W or minus W. But in practice, however, there is no signal that's exactly or strictly band limited. There is some sort of undersampling happening always, and some sort of aliasing that's always happening. So, aliasing refers to a phenomena where a high frequency component seemingly taking on the identity of a lower frequency. What does this mean? Let's say this is the spectrum of the original continuous time signal, and let's say we choose an Fs to be less than 2W. Now the spectrum will overlap, and the resulting spectrum, which is this solid line, is different from this original spectrum. And this frequency content, which is taking the identity of another frequency or appearing at different frequency location. So in this case, we have the aliasing distortion, in which results in that we cannot actually recover the original signal. If we use a filter here, the spectrum we're going to get is this solid line, not this one. We will not be able to recover the original signal because the spectrum is overlapping with each other. This is called the aliasing phenomena. So to avoid this aliasing phenomenon, you have to increase the value of Fs to move this spectrum to the right and this one to the left. We need to choose Fs larger than 2W in order to avoid this phenomenon. So to combat the effect of aliasing, we need to use two corrective measures. One, before sampling, we need to use a low-pass filter. It's called anti-aliasing filter to limit the bandwidth of the signal. If the signal is not strictly band limited and the spectrum is decaying gradually, we need to put a low-pass filter to force the signal to have a zero spectrum outside a certain band. And then we can sample the signal. Then the filtered signal is sampled at a rate that's slightly higher than the Nyquist rate, which we have said before for audio signals, the sampling rate is larger than 2 times 20 kilohertz. This larger sampling rate will ease the design of the filter, as we're going to see later on. So the use of sampling rate higher than the Nyquist rate will ease the design of the synthesis filter. So how is that? If this is the original signal, and we have sampled it with Fs that's slightly larger than 2W, so we have this guard band, we have this separation between the original spectrum and the repeated spectrum. This guard band will allow us to design a practical, realizable filter, so it doesn't have this sudden change. So we want the reconstruction filter to have a flat response between minus W and W, and then it should be decaying gradually until it reaches a very low value or very low response around Fs minus W and minus Fs plus W. This kind of reconstruction filter can be implemented physically, but this is happening because we have chosen Fs to be slightly larger than 2W, so introducing this guard band. Here the response of the filter is dashed between W and Fs minus W, indicating that it could take any shape. I don't really care what kind of shape in this part. I only want this part to be flat, and this dashed line I want it to decay to very low value, or ideally zero, at Fs minus W or Fs plus W, but I don't care much how this transition is happening. Is it happening this way, or a straight line, or that way? I don't really care much. So this concludes our lecture today, and in the next lecture we will start talking about the pulse amplitude modulation. Thank you.